All right, so today's notes are going to be about friction on an incline. And because we're doing friction on an incline, we actually get to have the definition, the proper definition of a normal force. Over the past couple of days, we've only been using the weight, but we actually have to use the definition of normal force properly. Remember that was F sub n. So here is the definition of a normal force. A normal force is, of course, a force, but it is a force that is perpendicular to a surface. I'm going to pause the definition right there in the middle just to make note of this. In typical English, the word normal means ordinary. Normal does not mean, oh, the projector's off. Normal does not mean ordinary in mathematics. In mathematics, normal means perpendicular for some reason. Anyway, Elon, if you like, you can just join the Zoom meeting until the projector turns back on. But yeah, just the definition of a normal force is that it's a perpendicular that is, a force that is perpendicular to a surface. But in this particular context, a normal force is perpendicular to a surface that is as a reaction to weight. You remember the old equal and opposite reaction line? You know, every force has an equal and opposite reaction force. There it is. That is technically true. Of course, technically, this is a physics class. Everything is technically true. But the normal force is the equal and opposite force to that. So let me draw you a picture of that. This would be for a flat and level surface. Here's what a normal force looks like on a flat and level surface. Flat and level surface. Object with mass. The weight of this object is down, okay? Downwards. And the weight is equal to mg. The equal and opposite force is what keeps it from breaking through the surface. That would be in the opposite direction with the same magnitude. But this time, it's the normal force. Do you remember that little right angle symbol that you use in geometry class? I'm going to add one, just so you know. That's perpendicular to the surface. That's on a flat and level surface. And that's why for the past couple of days, we've been able to use the weight, mg, in the equation for friction. But no more. But no more. Here is how we need to do it on an incline. So, for an incline at an angle theta. Here's the incline. That's the horizontal, so you have something to compare the incline to. And there's the angle theta. Let's put our box on the slope again. All right, just because it's on an incline doesn't mean that gravity decided to change directions. Gravity is still down. And just because it's on an incline doesn't mean that the normal force still points up. The normal force is still perpendicular to the surface. Those aren't equal and opposite anymore. See, those are equal and opposite. These forces right there. That's equal and opposite, which is what keeps things from moving when they're just sitting on a surface, right? I put my pen on the middle of the paper. The pen is putting weight into the paper. The paper is lifting it back up so that it doesn't move. Equal and opposite forces. There's no net force, so there's no acceleration. But if it's on an incline, not necessarily the case, but the normal force is still perpendicular. They're not equal and opposite anymore. The direction that this mass would go in would be that way, right? That's the way that it would go if it could go. But if it's not going, it must be resisted in the opposite direction. That would be this direction. Has anyone in this class ever seen a diagram of the four forces of flight? Thrust, drag, lift, weight. Ever seen that? That'd be like a 5th grade thing or something. Or maybe you know someone with a plane. I don't know. But yeah, that kind of reminds me of it. So that's the weight. That's the normal force. Okay? This is what is pulling it down to the earth. That is what is pushing it again, that's the force of the surface pushing back against it. What's this force that's stopping it from moving down the slope? It's the one we've been studying. It's friction. Okay, so this is kind of, intermediate trigonometry maybe, which means that I could go through the whole thing of how these are found, but rather than doing that, I think that might make more sense if everybody were in the room and you could, handle the watching Mr. S do math thing. I'm just going to give you the equations for them. The normal force is proportional to the weight because it's a reaction to it. However, it's greatest at 0 degrees and the least at 90 degrees. Which trig function is 1 here and 0 there? That would be cosine. And that means that the normal force is equal to the weight times the cosine of the angle of the incline. We've been doing all of our friction problems with a cosine of 0, which is equal to 1, and that's why all of our friction has been with just mg. But once you add in the incline, you got to deal with the angle, and that means that you've got to deal with a different normal force than the weight. We already know the equation for this. Okay, the equation for friction, we already know that. I'm going to go ahead and just write it in anyway. But it's the coefficient of friction times the normal force. But this one? Well, this one is going to be kind of complementary to this one. And I kind of literally mean complementary because it's at a 90-degree angle. That force is equal to mg times the sine of the angle. Okay, so we've got 4 forces here. I think I'm going to write that over there just so it's associated with it.